Hello and welcome to episode number 13 of CS350 Online. I'm your host as always, Leslie Eisted, and in today's episode, we are going to continue our discussion of virtual memory. Specifically, we're going to look at a kind of virtual memory known as paging, which you might actually remember from CS251, but if you don't, well, we're going to remind you of it today. Now, if you're following along with the textbook, you should probably read the paging section, but again, there's no pressure on reading the textbook. The other thing that I'd like to point out is that I've made a common OS161 error post. And this is a pinned post at the top of Piazza, and I really recommend that as you're working on assignment 2, make sure that you take a moment to read through the common errors that happen so that you don't spend weeks trying to debug something that's a fairly straightforward error to fix. So we've got things like the TLB miss errors posted, what happens if you're not getting any output, don't run tests back to back. And that's actually a really big one I want to mention to you just now, is that OS161's virtual memory system actually right now is really, really basic, and free doesn't actually do anything. Now, that may not mean much to you, but what it means is that when you free something, memory actually doesn't get recovered or reused. It's not possible in the current implementation. And the impact that can have on running tests in OS161 is kind of funny. For example, if you try to run fork test or SY2 back to back without rebooting OS161, you'll get really funny behavior, and it's very tempting to believe there's something wrong with what you've done. But if you ran it back to back, it's not to say you haven't done something wrong, it's just to say that you ran out of memory and the system misbehaved. So for each time that you run a test, you have to start OS161, run the test, and then shut it down, which is why I recommend doing the command line approach. That way you don't actually have to go through each of those phases in a manual sense. All right. So make sure you do read that post before you ask questions, because a lot of the questions are already common questions and common problems would actually be answered there. All right. So our OS of the day today is called OpenVMS, and this operating system has been around since 1977. It was originally produced by a company known as DEC or Digital, which doesn't exist anymore because it was bought by HP. Now, I got the old OpenVMS logo because the new one's kind of boring. And I mean, who doesn't like this like angry shark logo? I think it's a great logo for an OS. This operating system, what's interesting about it is how many different names it's had over its lifespan. I mean, when it was first being created, they experimented with different names like Star and Starlet, and then these long-winded acronyms like VAX11 VMS. VMS, of course, standing for Virtual Memory System, because that's one of the things they were focusing on in their implementation. But what's kind of cool about this operating system is, I mean, it is a time-shared operating system, so we do have concurrency. It does also support batch processing, but it has a built-in database as well, so it also supports transaction processing. Now, this operating system is not something you would have in the consumer. They did, for a very, very brief time, had like a desktop environment where it was like, here's just a personal computer. Let's run OpenVMS. That didn't take off so well. But it's primarily meant for servers, not really your desktop. And it supports a variety of different internet protocols, including something that's long deprecated called DECnet. It has a lovely distributed file system that has versioning, which of course is very nice. It has a lot of security. It does have a visual desktop environment, but again, it's not meant for the everyday user. It's more meant for the people who are maintaining and using the servers here. Now, what's really interesting about OpenVMS is it's an incredibly stable operating system. And there have been instances that have ran with OpenVMS without being reset or powered down for over 10 years. Can you imagine that? Like having your computer on and it ran and it never had to be reset and it never had to be shut down. Can you imagine not freezing? it's like this mythical unicorn kind of operating system. Because so I've got 3 different operating systems here kind of all sitting in front of me. I've got Mac OS and I've got Windows, and I've got a new Linux operating system. And I can tell you that my Mac freezes, I want to say every few weeks. It'll freeze or I'll have to reboot it. The Windows machine does updates so often that require rebooting. And I mean, you get blue screens of death on top of that. So that's not a very stable operating system. And the Linux one is reasonable, but you still end up with weird kernel panics and stuff from time to time. And you still have to reboot it from time to time. It's acting funny, reboot it, and it'll start behaving again. None of them are this stable, is the point I'm trying to make. And what's cool is, even though you may not have heard of OpenVMS and you might think, oh, it's an old operating system, nobody touches it, it's actually still under active development and people still use it. So it's not being developed for things like the processor sitting in front of you. They're not developing it for, the i6s, the i7s, the i9s. They're not developing this for the Ryzen line. They're developing this for the Itaniums. Because, again, this is meant for servers. It's meant for the big time. All right, so let's talk about, because it's been about 5 days, let's us actually talk about where we left off. We were talking about the wonders of virtual memory. Let's go back to full screen here. And just to kind of refresh where we were, we talked about what virtual memory is. It's the idea that we are going to abstract the physical memory addresses on your computer. And the reason why we want to abstract the physical memory accesses is kind of there's multiple reasons why we do this. One of them is that it is going to offer some isolation between the different processes. If every process believes that it has access to every address, then, i.e. it believes it has access to addresses 0 through the end of the address range, then it's not even going to think about there being other processes in existence, because according to that process, it's the king of the world and there's nothing else. So virtual memory gives us a really good way to isolate processes from each other. Because if you tried to access memory in another process, you'd just be accessing memory inside your own address space. And if it didn't actually turn out to be a valid address, then we find out that the MMU throws a lovely exception. So it does give us a really nice sense of isolation and protection. Now, that's the other interesting thing, is because we're using fake addresses, we can't just go around and start searching for things, other processes running. Whereas if we used physical addresses and we knew where we actually lived in real memory, then we know, by virtue of where we live, we know where we don't live, and we could start exploring things outside of our address range and find information we probably shouldn't be touching. So, I mean, it's really good for abstraction, it's really good for isolation, it's good for providing some security. But of course, it comes at a cost. It's not free. And the reason why it's not free is because if you have a fake address, these virtual addresses, your CPU doesn't know what to do with them. So because they're not real addresses. And if you tried to load a code, like an instruction, from one of these virtual addresses directly, you'd end up with garbage, because that's not actually where it lives in real memory. So the downside of virtual memory is the fact that we actually have to perform translations. We have to translate the virtual address to a physical address before the CPU is actually going to be able to do anything with that instruction. So and when I say the CPU can't do anything without the translation, I mean every single address you have ever seen until this course would have been an actual virtual address. Everything is a virtual address. Everything. That's an important thing to keep in mind. All right. And that means, yes, the program counter, everything would be virtual. Now, how do we perform that address translation? Well, the address translation gets performed by a special piece of hardware that actually lives on the CPU called a memory management unit, or MMU. And the MMU is going to give you some instruction as to what kind of addresses it supports and what kind of address translation schemes it supports. And then the operating system is going to have to implement virtual memory the rest of the way based on the specifications given by the MMU. So there's a bit of whatever the MMU states, the operating system kind of has to agree with that. And it's not to say that if the MMU it only supports X, that the OS has to support X, because sometimes you can, massage the data a little bit so that even though the MMU is still performing the same address translation scheme, the operating system can implement it slightly differently. So details there. We'll talk. OS 161 is doing this, by the way, and we'll talk about that some other day. So the MMU, what's going to happen is every single address that is seen, the MMU is going to take that address and it's going to convert it from a virtual address to a physical one. And the reason why we use hardware to do this translation is because it's faster. And if we tried to get the kernel to do this, then we'd have to throw an exception for every single address and have the kernel actually perform the translation. And that would be really, really slow. We'd get nothing done. Also, the kernel lives in virtual memory as well, and we'll talk about that another time. So that would just add to the complications. So we got hardware to do it because it's fast. All right. Now, we also talked about something called dynamic relocation, which is the most basic form of virtual memory. And the idea is simply we assume that the address space occupies some contiguous region of virtual memory. And we're simply going to find a contiguous block of equal size in physical memory, and we're just going to map one to the other. And then to perform the translation, we simply need the offset or relocation in physical memory, and we need to know the length of the data block. And then all you do is you check if the virtual address is less than the length of the block, and if it is, then you add the offset or relocation to the virtual address, and that gives you the physical address. And the beauty of this address translation scheme, it is blissfully simple. It's super efficient in terms of how much extra space you need to perform it, and it's super efficient in terms of time because you're doing a comparison and an addition, and that's very nice for each instruction. The downside, of course, is that address spaces aren't actually laid out like this. They're not just tightly packed contiguous regions. And even if they were, we end up suffering from a pretty bad fragmentation problem. Now, if our address spaces were these neatly tight packed contiguous regions, we end up with what's known as external fragmentation. And that is each allocation of physical memory is of a different size. And since we have the requirement that allocations are contiguous, we would end up with a situation where there is technically enough physical memory to hold the new address space, but because it's not contiguous, we can't actually allocate it. So we'd have to either do a defragmentation algorithm, which could be very, very slow, or we simply can't permit that process to be created. So you get external fragmentation with this implementation, along with a reduced number of processes that you can actually have residing in memory at any time, which of course reduces your degree of multiprocessing. Now, the truth is address spaces weren't actually laid out like that. They're not these tightly packed contiguous regions. Address spaces are actually laid out quite sparsely. So you have the code segment. This is, by the way, the OS 161's layout. So you have the code segment here, and then you have the data segment in this gold color, and then in this dark magenta color here, you actually have the stack. And this whole block here would be the entire virtual address range. Now, the remaining, you'll notice 50% of these addresses after the stack are actually not used. They're just not used by the user program. So technically speaking, of this 4 gigabyte maximum virtual memory address space, that's as big as it could be, we're actually only using 50% of it. Now, since we need to do a contiguous allocation, this would mean that every address space in OS 161 technically needs 2 gigabytes of space. That's actually going to solve the external fragmentation problem because every allocation would be of exactly the same size, but it also introduces a bunch of other problems. For example, so this is like, I think, sorts address space, and in total, if you add up how much memory it uses between the code, the data, and the stack, it's 1.2 megabytes. It's not very much. But we had to allocate, because we require a single contiguous allocation, I had to allocate 2 gigabytes of physical memory for it. So instead of external fragmentation now, I get internal fragmentation where I've got these large chunks of free memory that nobody else can actually use. And of course, when you've also got these really large allocations, you're also reducing the total number of processes you can load at any time. So while dynamic relocation is super easy and it does obey all the rules of isolation, protection, and efficiency, its fragmentation issues and reduced degree of multiprocessing make it not such a good choice, actually. Now, what we realized then was that since we only have these little segments in the address space that we're actually using, then why don't we just track these fixed number of little segments? And that was where the idea of segmentation came from. Instead of having one big contiguous address space, let's track the code segment, let's track the data segment, let's track the stack segment. And so we are going to divide our physical address or our virtual addresses into two components. The upper bits are reserved for the segment number and the lower bits are reserved for the address within the segment. And then the idea is we will store a limit and an offset for each of the segments. And then after we figure out which segment this address belongs to by looking at the upper bits, we will use the offset and limit for that segment to perform the translation. So it's just a tiny extension to dynamic relocation. There are advantages and disadvantages. So an advantage is that you get no internal fragmentation because you're only ever tracking the exact regions of virtual memory you use for your address space. So all of this space between the code and data segment, we don't need to track it because we're not using it. We don't allocate it. We don't keep track of it. We're only going to track the exact regions of the address space that we are actively using. The downside is that we didn't actually solve the external fragmentation problem because each segment will have a different size. That is, the code segment may be very small and the data segment might be very large, and then the stack would tend to be quite small as well. So we have an external fragmentation problem. That being said, what's really interesting, so this particular scheme I think has been around since the late 50s. And if memory serves me, so the first few versions of Windows didn't actually use virtual memory, but Windows 3 and 3.1 did, and they used segmentation. And even though there was an external fragmentation problem with it, it used segmentation as their virtual memory implementation, and there wasn't a problem with it. It wasn't a big deal. And I think it came down to, at the time, if you looked at how computers were being used with Windows 3.1 in the home and in the office, people were not running multiple processes at the same time. It was very unusual to run multiple things at the same time. It's not that you couldn't necessarily do that, but Windows 3.1 did not have preemptive concurrency. It didn't do time sharing. It did what's known as cooperative concurrency. So if a process did not explicitly yield or block or terminate, then there wasn't actually any sharing of the CPU going on, which is kind of interesting. And I mean, thinking back on both the UI of Windows 3.1 and the computers at the time, the concept of having multiple programs running at the same time just wasn't really there. I mean, the processing power wasn't there. Like, you're talking about 386s and 486s and maybe Pentium 1s if you were a little bit behind the time. And the amount of RAM, so on my 486, I had 30 megabytes of RAM. So and none of the programs were big. I know 30 megabytes today, that's like a photo, right? But back then, I mean, well, we didn't really have digital cameras. Or if you did, you were like super rich. I think I saw one digital camera in the 90s and it used like a floppy disk for storage. And it was really cool, but the photos were really bad quality. Like terrible, terrible quality. Because of course, how do you fit a big image onto a tiny little floppy disk that only fits 1.44 megabytes? The point I'm trying to make is that with Windows 3.1, it used segmentation, but the fragmentation problem never really became a real problem simply because the hardware didn't really support you running a lot of programs at the same time, and people didn't even think you could do that. So like you might have had 2 copies of Turing open or 2 copies of Notepad open, but I don't really remember ever doing anything crazy like having several Netscapes open. I don't think I ever had 2 programs really running at the same time until Windows 98, which would have been many years later. Okay. But anyways, segmentation, it does work. It does have external fragmentation, and under the right circumstances, there's no problem with it. It wouldn't work today, because if I think about the computer I'm using right now, I have, several hundred processes and thousands of threads. And today, of course, I decided I should probably close down my Chrome with all my tabs because I know there has been some audio-video sync issues, and that's actually due to my CPU throttling. Sorry about that. So I've just been trying to close as many programs as possible so it doesn't throttle too bad. All right. So this worked in the late 80s and early 90s for consumer hardware, but it doesn't work for today because we simply run too many programs. So what are we going to do? We really want to solve the external fragmentation problem because we want to make sure that we can run as many processes as possible. The way to solve the external fragmentation problem is to make sure that every single memory allocation is exactly the same size. Now, the only downside of that is if every allocation is the same size, then you're probably going to get internal fragmentation. So how do you mitigate that? How do you make the internal fragmentation as irrelevant as possible while solving the external one? And you kind of take the idea of segmentation to the extreme. What you're going to do, and this is paging, by the way, for those of you who are sitting at home, we're going to take physical memory, and we're going to logically, that is programmatically in code, subdivide physical memory into equal-sized chunks. And we call these physical pages or frames. Now, the size of frame really depends on your operating system and your architecture, but I can tell you that the most common frame size you will encounter is actually 4 kilobytes. 4 kilobytes. It's not that big. It's not to say that there aren't some systems using larger frame sizes, but as of the moment, and I want to say for the last maybe 20 years, 4 kilobytes has been the standard frame size. So you're logically dividing it into these equal-sized frames. It's all done in code. And you're going to do the exact same thing to virtual memory as well. So we're going to logically divide virtual memory into equal-sized pages. And the page and the frame size should be the same. It's not to say they can't be different, but life gets really complicated if they're different. It's not, I mean, you can deal with it, but it's much easier if your physical and virtual pages are the same size. So we're going to subdivide our virtual memory into equal size pages. And then what we're going to do is when we allocate memory for our address space, instead of allocating the exact number of bytes we need, we are going to round up to how many pages we need. So our address space goes from being 28 kilobytes to 7 pages. Okay? And that doesn't matter if it's a contiguously allocated address space or a sparse or a distributed address space. It doesn't matter. We're going to, for each segment of the address space we're actually using, we're subdividing it. We're now measuring it as how many pages do you take. And then the idea is fairly simple. For each page we use in the address space, we are going to map it to a physical frame of memory. And the idea is that each page can map to any frame. So we no longer have the requirement of large contiguous allocations. We're literally going to take each of these 7 pages of virtual memory, and I'm going to map them to any 7 frames of physical memory I can find, which solves the external fragmentation problem, because since all of my allocations are the same and I have no requirement that the pages are contiguous, I can just find any 7 frames to map them to, any 7. This is going to let us run more processes. It's going to let us use our physical memory more effectively. But there are some downsides. Now, number one, so we've gotten rid of external fragmentation. Downside, we do have internal fragmentation. But how bad is it, actually? So let's think about this. So OS 161 has 3-segment address space. We've got code, we've got data, and we've got the stack. Okay. You only use a page of virtual memory for your address space if you actually need it. So of those 3 segments, at most, since we have 3 segments, at most 3 pages might be partially filled. That means that maybe they're only half filled, or maybe they only have 25%. So that means, let's say you are only using 25% of 1 page for each segment. So that's your partial fill rate. Then that means I have 3 kilobyte loss for code, 3 kilobyte loss for data, and 3 kilobyte loss for stack. So in total, 9 kilobytes of internal memory is not being used. 9 kilobytes. I have 4 gigs of RAM. I don't care about 9 kilobytes. So yes, we have internal fragmentation, but it's actually really, really small. And if you were to expand that to a more common address space of like 5 or 6 segments, then what you'd find is like, okay, so you've got, somewhere between 5 and maybe 15 kilobytes of wastage, but you've got 128 gigabytes of RAM. Who cares? So yes, there is internal fragmentation, but it's so minimal that we don't care about it anymore. It's practically not there. It's irrelevant. But that doesn't mean paging is perfect. Paging is not perfect. The problem now is that since we've subdivided virtual and physical memory into these 4 kilobyte blocks, these pages and these frames, each individual page of the address space, we have to track, number 1, are we using this page of the virtual memory? And number 2, if we are using this page of virtual memory, what physical frame does it actually map to? We need something called a page table that maps every frame of virtual memory to the frames of physical memory that we're using. Now, some people always ask, well, why don't we just track the pages we're using? Why do we have to track every page of virtual memory, regardless of whether we're using it? If our address spaces were contiguously laid out, that is, all the segments tightly packed together with no space between them, then we wouldn't need to track every page of virtual memory. We could just say, okay, here's the page table, and this is the length of the address space. If the address is outside of the length of the address space, then it's invalid, and therefore not in the table. But the problem is that's not how address spaces are laid out. Address spaces are laid out with the code segment at the beginning, then some empty space, and then the data segment, and then a whole pile of empty space, and then the stack at the end. So as a result, we actually have to have one entry in the page table for every possible page of virtual memory, regardless of whether we're using it or not. And then in our table, we have something called the valid bit, and the valid bit is 1 if it's in use, that page is in use, and the valid bit is 0 if it's not in use. And then we're also going to keep track of, for each valid page, we are going to keep track of the frame number that page maps to. Now, in our example in the course notes, we have contiguously allocated address spaces. That's just for convenience sake. So what you can see here is, so the first process, which uses 28 kilobytes or 7 pages, has, since they're all contiguous together, has the first 7 pages of the page table valid, and then everything afterwards invalid. And then process B, which uses many more entries, has many more valids than non-valids. So then how does address translation work for this? Well, what you're going to do is we have a 2-part address again. I'm actually going to switch over here to my tablet. Hopefully it's charged up. I think it is. I know, you see, like, if you're looking at my Bluetooth table, it's like, why are there so many MX Master 3s? I don't know. For some reason, every time I, like, plug in my mouse, the MX Master 3 being my mouse here, it seems to think it's a new device. So there's like 20 of them in the list. It's bizarre. It's a feature. Broken feature. So let's go over to OneNote here once it bothers to open up on the wrong screen. Let's bring it back. I feel like there's no logic as to which screen OneNote actually opens up on. It's a very strange program. Okay. They keep releasing updates for OneNote, and I keep thinking to myself, oh, today'll be the day it works. It's never the day it works. It's never the update that fixes it. All right, so let's look at things here. We've got a two-part address now with paging. So if this is my virtual address, so there's my virtual address. I'm going to close this Chrome window over here. I don't think I need it. And I'm going to divide my virtual address, which has V bits, into two parts. And the highest order bits are going to be my page number. And the lower order bits are going to be the page offset. And the idea is that we use the page number, which is the highest order bits, as the lookup key in our page table. When I look up this page number in my page table, it's going to give me the frame number. And then I'm going to combine the page offset with the frame number to give me the physical address. Now, if we go back to the notes here, there's a bit of math at the bottom. And how do you actually do this math? Of course, now I've closed the tab that had all my formulas I wanted to show you. Oh, well. I'll go from memory here. So in order to get the page number, you take the modulo of the virtual address, or the virtual address modulo the page size. And that will give you, that gives you the offset, never mind. So to figure out your page number, you're going to divide the virtual address by the page number. And then to get the page offset, you take the virtual address modulo the page size. Now, I'm not sure you've seen this yet, but our addresses are given in hexadecimal. And I'm pretty sure nobody wants to do division and modulo in hex. So, okay. Either way, once you have the page number, you use it to look up the corresponding entry in the page table. You get the frame number, and then to compute the final address, you are going to multiply the frame number by the frame size, or page size since they're the same, and then you add the page offset. So, more math, all to be done in hexadecimal. Now, before you can actually do this, you have to check for validity. So when you get the page number from your address, you need to actually check the page table entry. And by the way, each one of these lines is an entry in the page table. You have to check to make sure that it's a valid entry. If it's an invalid entry, you throw an exception because it's not a part of your address space. If it is a valid entry, then that is when you get the frame number, you multiply it by the frame size, and you add the offset, and now you have your physical address. So your MMU, to support the translation of these addresses, is going to have one register really. And the register it has is the page table base register. And that register is simply a pointer to the, kids are playing soccer downstairs. It's kind of funny. So that page table base register is a pointer to the table in RAM, the page table in RAM. And then what you're doing is you use that pointer plus the page number to compute where the page table entry is. It's fairly straightforward, right? It's not too bad. But nobody wants to do division and modulo math with hex. So is there another way that we could look at this? And as it turns out, there is. If you actually look at what's going on in terms of the bits, we see that if we know how many bits the page number and page offset are, then we just take the upper order k bits, and that becomes the lookup into the table, and the frame number just because the upper order L bits in the physical address. And then adding the offset, well, the offset is the lower order M bits, and we're just dropping it down into place in the physical address. So, I mean, it's not that bad, right? Sorry, I just realized I was on the wrong slide. Now, the trick, of course, is how do you know how many bits you need for the page number, and how do you know how many bits you need for the page offset? Actually, that's pretty easy to know. There are some very simple formulas. So first off, there's a formula on 2 slides back that you should know. The maximum number of page table entries a page table contains is the maximum amount of virtual memory, not the size of your address space, the amount of virtual memory. Your address space is less than or equal to the amount of virtual memory you have. So we take the maximum amount of virtual memory, which is 2 to the power of v, and then we divide that by the page size, and that will tell you how many entries your page table has. And that's fairly straightforward, right? Now, then to figure out how many bits you need for the page number, it's simply how many bits do you need to index that page table? Well, the number of bits you need to index the page table is the log of the number of page table entries. So in this particular case here, we have a page table that has 16 entries. And the log of 16 is going to be 4. So we need 4 bits to index the page table, which means our page number for virtual memory is 4 bits. So the number of bits you need for the page number is always related to the number of page table entries you have. Now, the number of bits for the page offset, which is the address you have within the page, is actually related to the size of the page. So you just take the log of the page size. So in our case, we have 4 kilobyte pages. 4 kilobytes is 2 to the power of 12. You take the log base 2, the 2 to the 12, and you get 12 bits. So the lower 12 bits are our offset and the upper 4 bits are our page number. Now, that's because we're using 16-bit virtual addresses. Our physical addresses are 18 bits. And so when we perform the same math here, we find we need 6 bits for our frame number and we need 12 bits for our frame offset. And the reason why the offset is the same for virtual and physical is simply because the page size is the same for both. So it's going to be the same size. So that's some pretty cool math, right? And that is so much easier to do than doing division and modulo with hex addresses. All you have to do here is a bunch of logs and divisions with numbers and base with, 2 to the power of whatever. Much better. Much, 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 much better. Okay. So let's actually do an example here. And again, I'm not going to do all of these because I'd like you to have an opportunity to do some of these on your own. So let's look at just a couple of these virtual addresses. For process A, so I'm going to draw a little line here. OneNote has already crashed. Stop doing that. Okay, so what we have, let's use different color here. So we have our virtual address V, and then let's get our page number and our page offset, and then our frame, and then our physical address. So for virtual address 102C, now we know that from the previous slide that the page number is the highest order 4 bits. Remember, the highest order 4 bits, we're not referring to the number of hexadecimal digits, we're referring to binary. So we need to split this address, and we see that this is actually 0001. Oh, but wait a minute. Each hex digit is actually 4 binary bits. So for this particular example, it's that whole digit here. So this is actually page 1. And I look at page 1 and I check if it's valid. Page 1 is valid, so I can continue. Now my page offset is going to be the bits that are left. So my page offset here is 02C. And then I look up my frame number and I see it's 26. And then to make my physical address, I'm going to put this all together. 2602C. Oh, that's pretty messy C. Look at that. No crazy division. No crazy modulo. All we had to know is how many bits for page number and how many bits for the page offset. So let's look at the next address. The next address is 09800. Now the page number here is going to be, of course, 9, because again, this is the highest order 4 bits right here. And if I look this up in the table, I see that that's invalid. So we don't have a page offset, we don't have a frame number, and the MMU throws an exception. And anytime you are not able to translate the address, you write exception to indicate this is not a valid address. And then finally, our last address is, I'm going to make sure my zeros don't look like 6s. And it's funny because I tell my daughter that all the time, because she draws her zeros like 6s too. So we've got 0024. The highest, and I want to tell you that this address here could also technically be written as this. And it's very tempting when you see the second address here to think that the page number is the 2, but it's not. It's these bits are still here, even though that we haven't drawn them. The page number here is actually 0. So beware of that. We sometimes drop leading zeros. So page number is 0. I look up the valid bit for page 0 and I see that it's there. So my offset is 024. And then my frame number is 0F. And then I'm going to put that all together to get 0F024. That's not so bad, right? It's not so bad. It's pretty easy. All right. So is this what we do? No. This is not how we implement virtual memory today, because this has a pretty big problem. So before we talk about the pretty big problem, let's talk about some of the other things that a page table entry might contain. Number 1, we note that some segments of an address space might be read-only. For example, you have a code segment. Code segments should be read-only. By the way, they're not in OS 161. You'll fix it later. But code segments are supposed to be read-only. If you want to mark certain pages or certain regions of the address space as read-only, then in your page table entry, you should have a bit or a flag that indicates that addresses on this page are read-only. And that way, if the MMU tries to write or sees that you're trying to write to a read-only address, the MMU can throw an appropriate exception to say, hey, you're trying to write to a read-only address and you're not allowed to do that. Yes, it's your MMU that checks that, by the way. So we do have things like write protection bits. We also have some other bits that we use to track the usage of certain pages of the address space. So one of them is a use bit, and a use bit is simply indicating, has this page been used recently? So each time you use the page or use that entry of the page table to perform a translation, you would set the use bit to 1 to say, hey, I use this. Hey, I use this. And that's not useful right now, but when we talk about on-demand paging and using caches, that suddenly becomes very, very important. Another one that we do tend to use is something known as the dirty bit. And that is, have you changed the contents of these page? So every time the MMU recognizes you are trying to write to an address on that page, it would set the dirty bit to 1. And the reason why you might do that is even though our fork implementation automatically creates 2 separate address spaces, so we use ASCopy to make a brand new copy of the address space, that's not actually how modern operating systems necessarily do it. It's my understanding, and I might be a little off on this, so don't quote me on it, but some operating systems, when you fork, instead of creating a second address space, the 2 processes will actually share the address space until one of the processes starts to make changes to it. So, and then it will only create separate pages, like separate that region of the address space when one of them starts to write to it. So have the same thing like a write bit or a dirty bit will let us know, hey, I wrote to this, therefore you need to separate me. So I'm not affecting the other process. Why would you do that, doing that weird address space sharing until you actually write to it? Well, it saves space. Right? It's a bit more efficient. Operating systems are supposed to be efficient. All right. Now, that's not the problem. The problem we actually have with paging is the size of the page table. So first off, we know that a page table has so many entries in it. But did each of those page table entries actually consumes a certain amount of space? Now, we don't have a magical formula to give you to tell you how much space a page table entry is going to be. We will simply always tell you how big the page table entry is. For example, in OS 161, the page table entry might be 4 bytes each. So if we have each page table entry as being 4 bytes, then we can compute how much memory the page table actually takes in RAM. And in which case we take the number of pages, which in our case is 16, and we multiply it by the size of the page table entry, which is 4 bytes, and we end up with 64 bytes for each page table in the examples in the slides. Isn't that bad? It's not that bad, actually. Okay. But what about a system whose virtual memory and physical memory both use 32 bits? And let's assuming still that we use 4 bytes for each page table entry. Well, the number of page table entries we would have here is 2 to the power of 20. Yeah, it's a lot. And so with 2 to the power of 20 page table entries, multiplying that by 2 to the power of 2, that means we have 2 to the power of 22. That means that each page table with given a 32-bit virtual memory address length and a 4 kilobyte page size, each page table is 4 megabytes. Again, I'm not really upset by this because if I think back to, when I had a 32-bit computer, I had I think my last 32-bit machine had 512 megs of RAM. You couldn't actually run that many processes at the same time anyways, simply because of computational power and the amount of RAM. So it wasn't that big. But at the same time, if you think about a program like Hello World, whose address space might be 4 kilobytes, that's a lot of wasted space because the majority of the page table entries in that 4 megabyte table would actually be invalid. So it's kind of a space wastage. But let's take this one step further to the computer sitting in front of you right now. We are using currently 48 bits of virtual memory, unless you're one of those systems that has a GNU Linux kernel running at 57 bits for your virtual memory addresses. But let's assume you don't and you're using 48 bits like most people. 48 bits addresses for virtual memory and 4 kilobyte pages. So that's going to give you 2 to the power of 36 page table entries. Each of those page table entries, assuming they were 4 bytes in length, that is going to give you a page table size of 2 to the power of 38 bytes, which means your page table requires 256 gigabytes of RAM. What? That doesn't work. Because Hello World needs 1 kilobyte. 1 page. And you're telling me its page table is 256 gigabytes in size? Okay. So my latest research machine only has 128 gigs of RAM. The motherboard doesn't support more than that. I can't even fit 1 page table. And I'm going to guess that most of you don't have this much RAM either, so none of you can fit the page table either. The problem is these page tables the size of them gets out of hand really, really, really quickly. And the page tables live in RAM. They live in the kernel's memory. So you're saying that the page tables are enormous, live in the kernel's memory, but technically speaking, they're so big now they don't even fit. Not only that, since the address spaces of these programs is so much smaller, they're mostly invalid entries. Like, by mostly, I mean, they're 99% invalid. This doesn't make any sense. This is called single level paging and we don't use it. It might have been used many, many years ago, back in like the 60s and the 70s, when we used significantly fewer bits for addressing, but we don't do it anymore because we are using more and more bits for addressing, which makes the page tables exponentially huge. So we don't want to do that. So let's talk about what we do. What we want to do is have a better organization. We like paging because it gets rid of external fragmentation, but it also has the advantage of having so little internal fragmentation that we stop caring about it. But obviously having a single level table doesn't work because the table gets so big. The problem is that we're dumping everything into one table. Maybe think back to when you were a kid. I know, or maybe think back to someone you know who's maybe not a big computer person. They have the habit of dumping everything onto their desktop. I've seen desktop computers for people who are not programmers. Their desktop actually scrolls for like 5 or 6 pages. It's let's put everything in one directory. Come on in. One directory. That's all we have. Okay, that's what a single level page table is like. It's like dumping everything into one directory. You've got a billion things in one directory. What we want to do is to make things easier to find is we want to subdivide it into logical directories. So you might, for example, create a directory for files that start with each letter of the alphabet. And then for every file that starts with A, you put it in directory A. For every file that starts with B, you put it in directory B. But here's the trick. If you have no files that start with the letter L, then don't create directory L because you have nothing to put in it. And then you can take each of those directories and you could subdivide them into what is the second letter of the file name. That's a really bad organization scheme, but it is a good example of what we're going to do with our page tables. We're going to create multi-level page tables. And we are only going to create it's like a tree, there's a root, and we are only going to create a subtree if there is valid page table entries in it. If there's no valid page table entry anywhere as a leaf in that subtree, then we don't create it. So what we're trying to do with the multi-level page table is to reduce the total number of page table entries we have and to reduce the percentage of invalid entries. So we're going to reorganize the table into our hierarchy. So as an example, I've taken the very simple single level table and I've turned it into a 2-level table to show you how this can be advantageous. So our single level table for process A had 16 entries, of which only 7, so less than 50%, were actually valid. So we are wasting 50% of the space. If we take this table and we subdivide it into 2 levels, and we only create the subtables that actually have valid entries, we end up with a 2-level table. And if the table doesn't exist, by the way, your address will be null. to say there's nothing here. This is invalid. Any addresses that are here are invalid and non-existent. So we only create levels where things are valid. So in the upper level, instead of the page number giving you the frame number, the page number is going to give you a pointer to the page table on the next level. And it's only the leaves of this tree structure that will actually have the frame numbers. So in this case, we're going to put 4 page table entries into each leaf or each table. So 4, and then the next 4 go into here. So since the remaining 8 have nothing, we don't create subtables for them. So we are only going to have 2 tables at the next level. Now, in total, that means my 2-level page table has 12 entries. Just 12. So we've already reduced the total number of page table entries for this example. Furthermore, of those 12 entries, only 3 are invalid. So we went from over 50% invalid to 25% invalid. That's really good. That's a lot better. So how does this actually work? And does it guarantee that your page table will be smaller? So what we're going to do is instead of having one page number, we're going to have several page numbers. You will have a page number for each level of your tree. So if you have a 2-level tree, you will have 2 page numbers. And what you do to perform your address translation is the upper bits will be the root's page number, and so you'll look up the entry in the root. If the root says, in that page table entry, the corresponding entry, if it says it's invalid, then you throw an exception immediately because there's nothing down that tree. It doesn't even exist. But if, however, that page table entry says valid, then it gives you a pointer to the next level tree. And then you take the next bits as the page table and or the page number for the next table. And then in that one, in this case, since this is a 2-level tree, that's going to give us our frame number. And what's interesting is the math to compute the final physical address is the same. Once you have the frame number from the leaf, you are going to multiply it by the page size and add the offset. The offset doesn't change because the offset is related only to the page size. Easy, right? So now we're just having several page numbers that we use to traverse this tree of page tables. That's not that bad. That's actually a pretty good idea. But then the question starts to become, okay, so how does the translation work exactly? Well, as I said, once you have the frame number, the translation is exactly the same. The tricky part is the actual traversal of the tree to get to the frame number. So you're going to have an end part virtual address, and each of those beginning parts are going to correspond to page numbers for each different level of the tree. And this is kind of an iterative process. You start with the highest level page number. You do a lookup in that page table. If it's invalid, you throw an exception right away. If it is valid, however, it will give you the address of the next page table. And then you bring the next page number down and you do a lookup there. And you perform the check again. Is it a valid entry? If so, you get the next page number or the next address. And you pull the next page number down. But if at any point you get an invalid, you throw an exception right away. It's not too bad. But now the question becomes, how many levels do I need to have? Well, the overall goal of this, of multi-level paging, is we want to reduce the size of the page tables. We want to reduce the number of invalid entries stored in the page tables. And we have this goal, which doesn't make sense at this point in time, that we want each of those little tables to fit on exactly one page. Now, we know it doesn't make sense why it seems kind of arbitrary that we would have each page table fit on exactly one page, but let me explain why really quickly. and we'll talk more about it later. If a page table fits on one page, then when I'm doing on-demand paging and I need to load part of the page table from disk, instead of having to load several pages from disk, which is really slow because it's multiple I/O operations, I only have to do one. So in terms of performance, having each page table fit on a single page is actually a really good idea. Now, that means that if we have the goal of each page table fitting on a single page, that we are going to be using the page size as a part of our calculations to figure out how many levels we need. Now, just to give you an example here of, one where we realized we needed more space. If we had 40-bit virtual addresses and we tried to do this with 2 levels, we would realize that there are 2 to the power of 28 pages in virtual memory. And since we can only fit 2 to the power of 10 page table entries on each page, that means we need 2 to the power of 18 page tables that are leaves. That's how many leaves we have, 2 to the power of 18. And that means that the root has to have 2 to the power of 18 entries, but that doesn't fit on a single page, so we would need more levels. There's no explanation to this math here, but I'll show you some formulas in a moment. Which, by the way, aren't actually in the notes. So I'm going to open up OneNote now, and we will show you the lovely, lovely formulas. Let's get a new page. New page. For the record, I dual booted this Mac because I was so annoyed with this program not working in Apple. I was like, surely it works in Windows. So I dual booted it, using the official method that Apple suggests, under the hopes that would work. But unfortunately, the cooling system controller for Windows on Mac doesn't quite work properly, and so you end up running really hot, which was a whole other problem. So we're stuck with Windows. Stuck with Windows, or whatever this is. This is Mac OS. All right, so some very important formulas. And these formulas, by the way, are all in the virtual memory guide, which is posted in the extra content Piazza thread. So first off, we need to know how many page table entries fit on a page. Well, that's actually very easy. To figure out how many page table entries fit on a page, it is simply the page size, which is given, divided by the page table entry size, which is also going to be given to you. So, for example, if our page size is 4 kilobytes and our P2E size is 4 bytes, this is equal to, 2 to the 12. 4 kilobytes, by the way, is 2 to the 12, divided by 2 to the 2. So 2 to the power of 10 page table entries fit on each page. Okay? So that's the first thing we need to figure out. Real easy math, right? We are always going to give you the page size, and we're always going to give you the page table entry size. Don't have to worry about that. Okay. That's step 1. Ooh. Uh-oh. My battery died. Did it die? Yep, my battery died. Oh, that's not good. Okay. I'm going to switch over to VI here because my battery died and I can't draw with a mouse. Sorry, I would reach for my power cord, but I actually don't know where my power cord for this little device is. So let's open up VI because who doesn't like VI? So we've got page table entries per page is page size divided by PTE size. Again, both of those values are given to you, so that should be fairly straightforward. The next thing we need to know is number of bits for page number. So the page number, the number of bits you need for the page number is the log of how many page table entries fit on a page. So in our example that we did just a minute ago, we had 2 to the power of 10 PTEs per page. So the number of bits, page number bits, is equal to the log of 2 to the 10, which means I need 10 bits per page number. Yay, base 2 math. It's so much fun. Okay, the next thing that we need to know in order to figure that out, how many levels we need such that each page table fits onto a single page, is we need to know how big the page offset is. And we already know how big the page offset is. It's equal to the log of the page size. That's a G. Page size. Okay. So in our example, we have 4 kilobyte pages. So that's equal to 2 to the power of 12. So that means that the offset is log of 2 to the 12, which means 12 bits. Okay, now we have all of the information that we need to figure out how many levels our page table needs to have. So, again, this is not in your textbook. This is not in the slides. This is just some math I worked out, and yes, it works. It's totally valid. I'm giving it to you here, and it's also in the virtual memory guide on on Piazza. So the number of levels is I can't spell ceiling. The ceiling of V minus page offset. V, by the way, so I'll put it up here just so you remember. V is the number of bits used for the virtual address. It's V minus the page offset divided by the page number bits. So the number of bits you need for each page number. So, for example, if we had, let's say V equals 32, and let's say PTE equals size equals 2 to the 2, and our page size equals 2 to the 12, which is very typical numbers here, then we would have the bits for the page number equal to 20, because the number of entries, so I'll show you here how that actually works. Actually, just a minute. Give me a second here. It's not 20. That's a single level table. Going by memory here. So the page table entries per page is equal to 2 to the 12 divided by 2 to the 2, which is 2 to the 10. So then our bits for page number is 10, which means, and our page offset is going to be to the log of 2 to the 12, which is equal to 12. So then our levels is the ceiling of 32 minus 12 divided by 10. So that is, of course, equal to the ceiling of 20 divided by 10 equals 2. We need 2 levels for 32 bits. And on our modern computers that we have today, where we use 48 bits, and our PTE size, let's just assume it's still 4 bytes. I think it's actually 8, but let's pretend it's still 4. And our page size is still 4 kilobytes. Then we have page table entries per page is still, because the PTE size and the page size hasn't changed, it's still going to be 2 to the power of 10, which means that our bits for a page number is still 10, which means, and our page offset, since the page size hasn't changed, is still 12 bits, which means the number of levels for this is the ceiling of 48 minus 12 divided by 10. So that is the ceiling of 36 divided by 10, which is, of course, 4. And yes, that is, by the way, the answer to how many levels page tables on your computer have right now. So yes, modern operating systems are using multi-level page tables, and the size of those page tables is, or the height of them is 4. Exciting, right? All right. Now, is this perfect? Is multi-level paging always going to give you a total page, like the size of its page table in total, is that always going to be smaller than the single level table? No, it's not. This works because most processes don't use more than a small amount of the virtual address range. However, there is a point at which the multi-level table is sufficiently full such that the total amount of space the multi-level table takes is greater than the size of the single level table. So for example, if you used every page of virtual memory, the multi-level table would be significantly bigger than the single level page table. It's kind of interesting. And by the way, you can figure that out mathematically, the difference in size if you used every page. And you could probably also quite easily figure out at what point do you cross the line where the multi-level table's total size is bigger than the single level tables. The only reason why we're using this and claiming that it works is because we don't reach that threshold. But technically it is possible, for the record. All right, I'm going to leave that here for today. We are going to talk about one of the other problems with multi-level paging in our next episode on Thursday. And then we are also going to start talking about how OS 161's virtual memory works. So we will see you all on Thursday. And hopefully you like our little game of the day. I'm sure many of you have actually played it before.